Hello friends, hello. I hope you are doing well. I welcome you to this episode that is Learning Physics with me. And today I want us to look at ideal gases, temperature and thermodynamics. And specifically, I want us to concentrate on the solutions to past paper questions. This is actually part 3. You have seen the questions in part 1, the questions in part 2. They're not so much different from the ones you are going to see in part 3, but this is just to make sure that we gain enough confidence in answering these questions. That's why the videos will be so many, because the document that you have with these past paper questions is having so many pages under this unit of ideal gases, temperature and thermodynamics. Okay, so the last time we were here, or in part 2, we must have stopped on this page, 436. So I want us to resume from page 437, and we were trying to attempt this question. So a fixed mass, I think I need to check to get a pen. So a fixed mass of a gas has an initial volume of this 5.00 times 10 power negative 4 meters cubed at a pressure of 2.400 times 10 power 5 pascals and a temperature of 288 Kelvin. It is heated at constant pressure, so that in its final state the volume is 14.5 times 10 power negative 4 meters cubed at a temperature of 835 Kelvin as illustrated. So the only thing you can notice is that the pressure is actually remaining constant. Show that these two states provide evidence that the gas behaves as an ideal gas. So if the gas behaves as an ideal gas, then PV over T should be equal to a constant, because we said an ideal gas is a gas which obeys the equation PV equals to nRT. So if the gas is ideal, then PV over T should be equal to nR, where this is a constant. So we are just going to try and verify that. Let's start with the first stage. I'll call this one P1, V1, T1. So let's check P1, V1 divided by T1. This would be equal to we are substituting the values. So this pressure is 2.4 times 10 power 5. Volume is 5.00 times 10 power negative 4 divided by the temperature, which is 288. So that gives us, let's press the calculator. So this gives us 0.417. Let's check P2, V2 divided by T2, that is for the second stage. The pressure is 2.4 times 10 power 5. The volume is 14.5 times 10 power negative 4 divided by 835. Let me press the calculator. I'll try to maintain the same number of significant figures as the one I've just used. So this is also giving me 0.417. So it is giving an impression that P1 V1 divided by T1 is equal to P2 V2 divided by T2. So we can conclude that this is equal to a constant. So if PV over T is a constant, PV over T is a constant, then this must be an ideal gas. It is an ideal gas. PV over T is a constant, so it is ideal gas. Okay, let's continue. The total thermal energy supplied to the gas for this change is 569 joules. Supplied to, so this should be positive. That should be positive according to the sign convention. Determine the external work done. When you look at the volume, you see that the volume is increasing. So in your mind, you know that this work done will be negative according to convention. Expansion will result into an increase in volume. So this work done is going to be negative because the system is doing work to the surrounding. So the work done, W, is going to be pressure times change in volume. When we substitute, this will be 2.4 times 10 power 5. Then the change in volume is 14.5 minus 5.00, which gives us, okay, this is times 10 power negative 4. And when you press your calculator, so this is giving me 228 joules to three significant figures. So the work done is 228 joules. I'm saying this work done is going to be negative because of the expansion. Then the next part of the question, the change in internal energy of the gas. State whether the change is an increase or a decrease. So change in internal energy by the first law of thermodynamics, this will be equal to the heat by heat supplied plus the work done. The heat is added to the system. We said it is already positive, 569. The work done is negative because the system does work the surrounding, and this gives us 341. You notice that this is positive. It is a positive value. So this is 341. 941, yes. So the change in internal energy is positive, and a positive change in internal energy means an increase. So they said state whether the change is an increase or decrease. So because it is positive, so this is an increase. Okay, that is very easy. Next, state what is meant by an ideal gas. We said for an ideal gas, it should obey the equation. So this obeys the equation PV equals to nRT at all temperatures, and pressure, where P is the pressure of the gas, V is the volume of the gas, and T is the absolute temperature. Of course, N times R, this one is a what? A constant, because N is the number of moles and R is the molar gas constant. So N times R makes that constant, number of moles and the molar gas constant. So that is an ideal gas. Next, that is part B. The mean square speed of an atom of a fixed mass of an ideal gas is given at this temperature is given as that. The gas is heated at a constant volume to a temperature of that. When the volume is constant, those who remember, the pressure is directly proportional to temperature. Determine the rise in Kelvin of the temperature of the gas. The rise in Kelvin of the temperature of the gas, of course, we started with 32, then 80. The change in temperature on the Kelvin scale is the same as the change in temperature on the Celsius scale. So I just subtract, and that gives me 48. I don't need to again add 273 on 48, not at all. Then determine the root mean square. Determine the root mean square speed of the atoms at 80 degrees Celsius. at 80 degrees Celsius. They have given us the root mean square speed at 32 degrees Celsius. If you remember, the translational kinetic energy of the molecule average was equal to 3 over 2 times kT. And this meant that a half m average of c squared is equal to 3 over 2 times kT. Then it means the mean square speed is directly proportional to the temperature. In other words, it is equal to a constant times, I don't want to use this constant k, because people will think I've taken this, not at all. So the mean square speed is equal to a constant, not this k is not Boltzmann's constant, just a constant of proportionality. Maybe let me write here directly proportional to t. So I'm going to introduce there is a constant there. So mean square speed is equal to a constant times t. So for the first case, since the second case is the one which is required, I'll put it on top. So the mean square speed which you want for the second case is equal to a constant times the new temperature, which is 80 plus 273 to change it to Kelvin, divided by the original conditions where the mean square speed was given. They gave us the mean square speed as 1.9 times 10 power 6. So this will be equal to a constant. Then the temperature was 32 plus 273. So if I try to find, of course, to find the root mean square speed, I'll find the square to both sides, but the constant has cancelled out. So the root mean square speed will therefore be equal to the square root of, this will be for this temperature, this is 353, divided by, for the other temperature is 305, then times, of course, I've found the square root. So I found this, remember this was mean square speed, this was squared. So if I have found the square root, then this will be times 1.9 times 10 power 6. So it is also under square root. Then you press your calculator. Let me press mine. 353 divided by 305 times 1.9 exponent 6. Then square root of the answer. So I'm getting 1482.9, which to three significant figures is 1480. To three significant figures. You can verify. Then next question. State an expression in terms of work done and heating that is used to calculate increase in internal energy. So we know increase in internal energy is equal to Q plus work done, but I can't write that because that can't give me 2 marks. So I will say, they said state an expression in terms of work done and heating that is used to calculate the increase in internal energy of a system. So I will choose one side of the sign convention. So I will say increase in internal energy is equal to thermal energy absorbed or thermal energy added to the system, or heat energy gained by the system, or heat energy transferred to the system. That is heat energy transferred to the system plus the work done on the system. So I have defined the sign conventions very clear. Alternatively, you could also give otherwise sign conventions. Me, I have taken, increase, positive, heat energy transferred to the system, that is positive, work done on the system, that is also positive. Okay? State and explain in terms of your expression in A the change, if any, in the internal energy of the water in an ice cube when the ice melts at atmospheric pressure to form a liquid without any change in temperature. If there is no change in temperature, state and explain in terms of your expression the change, if any, in the internal energy of the system. There is no change in temperature. That means the kinetic energy of the molecules does not change. Therefore, even the average does not change. But then, during melting, the volume decreases, meaning work is done on the system. So thermal energy is absorbed to break the lattice structure of the solid, and that thermal energy is what we call the latent heat of fusion. Therefore, the internal energy increases because the potential energy part increases. So volume decreases, volume slightly decreases, volume decreases, volume decreases. So the volume decreases, so work is done on the system. The volume decreases, so work is done on the system. Work is done on the system. Thermal energy is absorbed to break the lattice structure. So the internal energy increases. Internal energy increases. On the other hand, you can look at the volume change. Of course, many times some solids, when they melt, their volume occupied tends to decrease. So there's a little decrease in volume. So the work done on the system, there's work done on the system, because they said at atmospheric pressure to form a liquid without any change of temperature. So the pressure is most likely going to do some work onto the solid, on the system, as the ice melts. On the other hand, also the volume could slightly increase as the bonds are slightly broken between the molecules. So what is very important is that thermal energy is absorbed to break the lattice structure or to break the bonds, so that internal energy increases. Of course, the kinetic energy of molecules does not increase. Kinetic energy of molecules does not increase, does not change. Kinetic energy of molecules does not change, but the potential energy component, the potential energy slightly increases. That's what increases the internal energy, because remember, the change in internal energy is equal to the kinetic plus potential energy of all the molecules. Even if the kinetic energy is not changing, but if the potential energy changes because work is done, then internal energy increases. Some people would want to think about this in terms of volume increase when a solid, when a liquid melts. When a solid melts, So many people prefer to think about this as an increase in volume. And if there is an increase in volume, then work is done by the system. So you would also say on the other side, if you consider an increase in volume and say volume increases, but this is slightly. Volume increases slightly. Volume increases slightly, so work is done by the system. Thermal energy is absorbed to break the lattice structure or to break the bonds. Thermal energy is absorbed to break the bonds between molecules. So it means the potential energy component increases even though the kinetic energy of the molecules does not change. And if the potential energy increases, then the internal energy increases. Maybe let me rephrase this for some of you. For some of you, I want to make this one easier for many people because I know when I give two alternatives, some people prefer one side and therefore they get confused. Yeah, you can rub. I want this video to be extremely natural. To be extremely natural. So during melting, volume slightly increases. Volume slightly increases. Volume slightly increases. So work is done by the system. Work is done by the system. So we say potential energy increases. Potential energy increases, but kinetic energy does not change. Does not change. And if kinetic energy of the molecules does not change, but potential energy has increased, remember internal energy, the change in internal energy will depend on both the kinetic and the potential energy of the molecules. So that means internal energy increases. Internal energy increases. Internal energy increases since thermal energy is absorbed. Since thermal energy is absorbed to break the bonds or to break the lattice structure, to break the bonds. To break the bonds between molecules. So this thermal energy is the latent heat of fusion. This is the latent heat of fusion. So this is the latent heat of fusion. Okay, so let's proceed. Then also state and explain in terms of your expression in A, the change, if any, in the internal energy of the gas in a tire when the tire bursts, so that the gas suddenly increases in volume. Assume that the gas is ideal. The gas suddenly increases in volume, so in other words, the gas expands. The gas expands, so if the gas expands, it means work is done by the gas. So work is done by the gas. Of course, this work is done by the gas against the atmospheric pressure or against the atmosphere. And since no time for thermal energy, because they said suddenly, the gas suddenly increases in volume. So there is no time for thermal energy to enter or leave the gas. There's no time for thermal energy to enter or leave the gas, but remember change in internal energy is Q plus W. The volume is increasing, it means the work done is negative. There is no time for thermal energy to enter or leave the gas because it happens suddenly, so Q is 0. This is negative, Q is 0, it means change in internal energy is negative. So it means internal energy decreases. So the gas expands, so work is done by the gas against atmosphere or against the atmosphere. There is no time for thermal energy to enter or leave the gas, meaning that the change in internal energy is negative, which is a decrease. So internal energy decreases. Internal energy decreases. I hope that is easy to understand. The gas expands, meaning it does work to the surrounding, that is work done is negative by convention. Because this happens suddenly, there is no time for thermal energy to enter or leave the system, that is adiabatic. So Q is 0. That means change in internal energy is just equal to the work done, which is a negative value. A negative value of work done will give us a negative value of change in internal energy, and negative value of change in internal energy means a decrease. Therefore, the internal energy decreases. Okay, next. State an ideal gas con is said to consist of molecules that are hard, elastic, identical spheres. State two further assumptions. There are so many. This time I will only state very few. Number one, there is a large number of molecules. We assume that there is a large number. We always assume that there is a large number of molecules. So an average behavior is always considered. We also assume that the molecules are in continuous random motion. The molecules are in continuous random motion. An average behavior is very important. We also say that there are no intermolecular forces. No intermolecular forces of attraction or repulsion except during collision. Except during collisions. So when two molecules collide with each other, that's when we can think that they have come close enough for the forces to act. Number four, we can also assume that the time of collision or the duration of collision is very small compared to the time between collisions. So the time of collision is negligible compared to the time between collisions. Another one, we said the total volume of molecules is negligible compared to the volume of the container or the containing vessel. Where can I put that? Let me put it here. The total volume of molecules. When you add the volume of all the molecules, you notice that the total volume of the molecules is negligible. It's too small compared to compared to the volume of the containing vessel. Okay, so those are the assumptions. I think they are now part of us. We don't need to think much about them. In a real gas, the number of molecules per unit volume in an ideal gas is given as n. It is assumed that all the molecules are moving with a speed v. It is just assumed. The pressure P exerted by the gas on the walls of the vessel is given by this expression here. Remember, N is the number of molecules per unit volume. N is the number of molecules per unit volume. Okay, explain the reasoning by which this expression is modified to give the formula P is equal to a third N. Remember, N is the number of molecules per unit volume. In other words, small n is the number of molecules per unit volume. Explain the reasoning by which this expression, this one here, is modified to give the formula, this formula here. So we said in a real gas, there is a range of molecules move randomly with a range of velocities. So we must take the average value, or we must take an average of their velocities or of their speed. That's why we come up with this. So we can say in a real gas, in a real gas, in the gas or in a real gas or in an okay, I can even say in an ideal gas, there is a range of velocities. In an ideal gas, there is a range of velocities. In other words, gases move with a wide range of velocities, or molecules of gases move with a wide range of velocities. So an average behavior, an average behavior of v squared must be taken. So we must take the average. We must take the average of v squared. So in an ideal gas, there is a range of velocities. So we must take the average, but of course, even if you refer to a real gas, because in practice, we just approximate real gases to be ideal. So I can say in a real gas, there is a range of velocities. So we must take the average of v squared. Okay. So the answer there is because the molecules move with a wide range of velocities. So that's why we need an average of the value of the speed. Then part C, the density of an ideal gas is given as 1.2 at a pressure of 1.0 times 10 power 5 pascals and a temperature of 27 degrees Celsius. Calculate the root mean square speed of the molecules of the gas at 27 degrees Celsius. So they have given us, we know that P is equal to, they have given us a third times n times small m times mean square speed. But remember, small n, this is the same as a third. Small n is capital N over V, that is number of molecules per unit volume, then times m times mean square speed. Of course, this is n times m is total mass over volume. This becomes density. So it is precisely the same as saying P is equal to a third times density times c squared. So I can now substitute quantities. The pressure is given as 1.0 times 10 power 5, which is going to be equal to a third times the density, which is 1.2, times the mean square speed, So if I try to find the mean square speed, let me press my calculator. So finding the mean square speed, this is giving me 2.5 times 10 power 5. Of course, this will be meters squared per second squared. Then the root mean square speed, I'll find the square root of this value, that is 2.5 times 10 power 5. So this is giving me exactly 500 meters per second. Then calculate the mean square speed of the molecules at 207 degrees Celsius. So we have already seen that the mean square speed of molecules is directly proportional to the temperature. We have calculated the mean square speed at the root mean square speed at 27 degrees Celsius, and we have also the mean square speed at that temperature. So I'll just introduce a constant. So I'll first find, we want the mean square speed. So the mean square speed will be equal to a constant times the temperature, which is 207 plus 273. What is that? 207 plus 273, 207 plus 273. That is 480. So this will be times 480. 480, then divide by, here we go, the mean square speed as 2.5 times 10 power 5 at a temperature of, that was 27 plus 273, which is 300. So that is 300. So the constant has cancelled out. So we now get the mean square speed. Let me press my calculator. 480 divided by 300 times 2.5 exponent 5. So this is giving me 400,000, which is 4.0 times 10 power 5 meters squared per second squared. Okay, next. Two bodies are in thermal equilibrium. State what is meant by thermal equilibrium. We say two bodies or two parts of a body are said to be in thermal equilibrium when they are at the same temperature, and there is no net flow of thermal energy or no net transfer of thermal energy between the two bodies. So one, thermal equilibrium, bodies are at the same temperature. The bodies are at the same temperature. The bodies are at the same temperature and there is no net transfer of thermal energy. No net transfer of thermal energy between the bodies. There is no net transfer of thermal energy between the bodies. Part B, the temperature of a body is found to increase from 15.9 to 57.2. Determine in Kelvin and to an appropriate number. I love this part here. An appropriate number of decimal places. The rise in temperature. Rise in temperature, that is the difference in temperature. Remember, difference in temperature on the Kelvin scale is the same as difference in temperature on the Celsius scale. So we just subtract, and this is 41.3. Because the temperature is given to one decimal place, I will also quote this to one decimal place. Then the final temperature. The final temperature is 572.7.2 and it is given to one decimal place. So when I'm converting, I'll add 273.15. 57.2 plus 273.15. This gives me 330.35. But the temperature was quoted to one decimal place, so I round off this to one decimal place, 330.4. Okay. An ideal gas at a constant pressure of this is heated from a temperature of 290 to a temperature of 350. The change in volume of the gas is given as that. So that is the change in volume. The total change in kinetic energy measured in joules of the gas is given by this expression. Determine the thermal energy required to produce the change in temperature from 290 Kelvin to 350 Kelvin. Determine the thermal energy. So for one molecule, the change in kinetic energy is equal to 3/2 times 1.9 times the change in temperature, which is going to be, this is, what is the difference? 350 minus 290. 350 minus 290. So this is going to be equal to, press the calculator, 1.9 times, I think this is 60, 290, 350 minus 290, that is 60. So when I press, I get 171 joules. Then, but they want the thermal energy required. So remember, the change in kinetic energy is equal to the change in internal energy. The change in kinetic energy is equal to the change in internal energy because the gas is an ideal gas. The kinetic energy of the molecule, total kinetic energy of the molecules is equal to the change in internal energy, or is equal to the internal energy of the gas. So the change in internal energy is going to be the same as the change in kinetic energy of the molecules. Okay? Then we can find the work done because remember, the change in internal energy is equal to Q plus work done. Now we have the change in internal energy. All we need is the work done to be able to find the thermal energy required. So work done is given by pressure times change in volume. And this is going to be, the pressure is given as 1.2 times 10 power 5. The change in volume is 950. I change it to meters cubed. To be 950 times 10 power negative 6. And this gives me, press your calculator. So this is 114 joules. That is the work done. So we just need to substitute now. But note that there is, determine the thermal energy required to produce the change in temperature from 290 Kelvin to 350 Kelvin. There's an increase in temperature. There is an increase in temperature. Temperature is the average kinetic energy of the molecules that make up the system. temperature is the average kinetic energy of the molecules that make up the system. The change in volume, an ideal gas at constant pressure is heated from a temperature of that to a temperature of this. The change in volume of the gas is this. Most likely the gas is expanding. So that means the work done is negative. So this work done is negative because it seems like the volume is increasing by 950. So this work done will be negative. So I can now substitute internal energy 171 is equal to the heat supplied or thermal energy required plus the work done, which is negative. So the work done is negative 114 joules. So when you make Q the subject, Q will be equal to 171 plus 114. And when I add this, so this is 285 joules, approximately 290 joules. So note, they say the total change in kinetic energy measured in joules of the gas molecules was given by this. So I found the change in kinetic energy, and I knew total kinetic energy of the molecules is equal to total internal energy. The change in kinetic energy will be the change in internal energy. Then I found the work done. I substituted in the first law of thermodynamics to be able to obtain the thermal energy required. Okay, next. An ideal gas has pressure. Pressure is given as this, volume is given as that, and temperature is given as that, as shown in the figure. You notice that the volume is not changing. Very straight away, when you see that the volume is not changing, it means there is no work done. Change in volume is 0. That means the work done is automatically 0. And when the volume remains constant, in your mind, you know that the pressure is directly proportional to temperature. Pressure is directly proportional to temperature. I think that was called pressure law. Okay. Then a change in energy of gas to 40 joules results in an increase of pressure to a final value of 5.0 times 10 power 5. The thermodynamic temperature becomes T. Calculate the value of T. So that one, since the volume is constant, we shall simply say that the pressure is directly proportional to temperature. So P1 over T1 is equal to P2 over T2. So we want to find T. T2 is T actually. So this will be P1, the first pressure, which is 5. The first pressure is, no, I want to find the T2, so I need P2, pressure P2 is 5.0 times 10 power 5, divided by pressure P1, which is 1.0 times 10 power 5 from the above diagram, then times the temperature T1. T1 was given as 300 Kelvin, so this will be times 300. So this just substitute, just press my calculator. So that is 5 times 300. I don't need calculator for this. This is 1500 Kelvin. Therefore, we can conclude that the temperature T is 1500 Kelvin. Then amount of gas, that is number of moles. Number of moles is equal to PV divided by R times T. I can use the first stage. So that will be 1.0 times 10 power 5 pressure. Then times volume 4.0 times 10 power negative 4 volume. R is 8.31. Temperature is 300 Kelvin. I just press my calculator. Okay, so this is giving me a 0.016 to two significant figures. Alternatively, you could also use the second stage where the temperature is 1500. And I believe you'll get approximately 0.016 moles. Okay, the increase in internal energy of a system may be represented by this equation. Remember, plus Q was heat energy supplied to the system, or heat transfer to the system. Heat transfer to the system. Thermal energy absorbed by the system. Heating energy supplied to the system. So it is it is all ending up into the system. Then positive W, that is work done on the system or to the system. So this is work done on or to the system. The work done on or to the system, I think that is the sign convention that we are familiar with. Okay, next. State for the gas in A the value of delta U, that is change in internal energy. Let me take you back here. Change in internal energy. That is state for the gas in A, change in internal energy. So they say that change in energy of the gas of 240 results in an increase of pressure to a final value of that at constant volume. At constant volume. So the change in internal energy, remember, is equal to Q plus W. Volume is constant, work done is 0. So change in internal energy is just equal to the value of Q. So this is going to be 2, because it is added, it is positive. So it will be plus, this will be positive 240 joules. Then, of course, this one is still the same, plus 240 joules. Then the work done, of course, that one is 0 because the volume is constant. The work done is 0 because the volume is constant. If you want to verify, you can just substitute change in internal energy is equal to Q plus work done. This one is 240. This one is 240, so the work done is 0. Okay, that one is done. Next, the equation of state for an ideal gas of volume V at pressure P is PV is equal to nRT, where R is the molar gas constant. State what is meant by the symbol N. Of course, N is the number of moles. Number of moles. Or you could say amount of substance. Amount of substance. Then T, this is strictly absolute temperature. It is strictly absolute temperature or Kelvin temperature or thermodynamic temperature. Absolute temperature or Kelvin temperature, temperature in Kelvin units. Or thermodynamic temperature, that means the same. An ideal gas is held in a container of volume 2.4 centimeters times 10 power 3 centimeters cubed at a pressure of 4.9 times 10 power 5 pascals. The temperature of the gas is 100 degrees Celsius, that is 373 Kelvin. Show that the number of molecules of the gas in the container is this. That is very easy. Number of molecules. First of all, we know that PV is equal to nRT. And we know that number of moles is number of molecules divided by Avogadro's number. So times R times T. I think that is even enough for me to find N. Because Avogadro's is known, R is known, T is known, P is known, V is known. Alternatively, you can replace R over N with K if you want. But let me stop at that point. And I say the number of molecules will be equal to PV times Na divided by R times T. I'm substituting. Pressure is 4.9 times 10 power 5. Volume is 2.4 times 10 power 3, but it is in centimeters cubed. So I will say times 10 power negative 6 to change it to meters cubed. Avogadro's number is 6.02 times 10 power 23. This is divided by 8.31 times the temperature was 100 degrees Celsius, which is 273 if you change it to Kelvin. Press the calculator. Okay, my calculator is exactly giving me 2.3 times 10 power 23 to two significant figures. You can also verify with your calculator. Use data from B to estimate the mean distance between molecules in the gas. Use data from B to estimate the mean distance between molecules in the gas. Let's see which data do we have. An ideal gas is held in a container of this volume at a pressure of that. So we want the volume occupied. So the volume occupied by one molecule, if the gas of the container has this volume, and we assume that the atoms fill up or the molecules fill up the whole container, then we can assume that the volume occupied by one molecule, the volume occupied by one molecule, volume occupied by one molecule, no, not one molecule, volume occupied by, because this is, okay, volume occupied by one molecule is approximately going to be equal to the total volume there is 2.4 times 10 power 3 divided by the number of molecules, which is 2.3 times 10 power 23. This is going to be equal to 1.04 times 10 power, which power is that? 2.4 times 10 power negative 20 centimeters cubed. That will be the volume occupied by one molecule in a container. Then, but remember, the molecules move randomly in 3 dimensions. So if we want to find the mean spacing, this is the volume occupied by one molecule. So this is centimeters cubed. Then if I want the mean spacing or the average spacing, we saw the interatomic spacing, so I will find the cube root of this value here. So I will simply say that the mean spacing is approximately going to be equal to the cube root of 1.04 times 10 power negative 20. And when you press your calculator, cube root, this is approximately 2.2 times 10 power negative 7 centimeters. So because it is an estimate, I'll just write this as 2 times 10 power negative 7 centimeters as my estimated mean distance between the molecules in the gas. Okay, next. Again, state what is meant by internal energy. That is the sum of the random distribution the sum of the random distribution of the potential energy and kinetic energy. Potential energy and kinetic energy of all the molecules making up the system. The sum of the random distribution of potential energy, potential and kinetic energy. I want to put the word energy here. Potential energy and kinetic energy of all the molecules making up the system. Okay. Explain by reference to work done and heating whether the internal energy of the following increases, decreases, or remains constant. In part 1, the gas in a toy balloon when the balloon bursts suddenly. Suddenly. If it bursts suddenly, the process is adiabatic. There is no time for heat to enter or leave the system. So suddenly it means no time for heat to enter or leave the system, to enter or leave the gas. That's why it bursts suddenly. If they said suddenly, then there is no time for heat to enter or leave the gas. So that means Q is going to be equal to 0. Q is 0. But then, whether the internal energy of the following increases, decreases, or remains the gas in a toy balloon when the balloon bursts suddenly. So if no time for heat to enter or leave the gas, and work is done by the gas against the atmosphere as it expands, then internal energy decreases. So work is done by the gas against the atmosphere as it expands. As it expands, because work is done, that work done is negative, so W is negative. W is equal to a negative value. So you can now look at the change in internal energy being equal to Q plus W. Remember, this is 0, this is negative, meaning this is negative. That is a decrease. So we simply say internal energy decreases. Ice melting at constant temperature and at atmospheric pressure. Ice is melting at constant temperature and at atmospheric pressure to form water that is more dense. It is forming water that is more dense. It is forming water that is more dense. It is forming water that is more dense than the ice. Density is equal to mass times volume. Mass over volume. So what has increased then? If here they are telling us it is forming water which is more dense. Normally, in one of the examples, I wanted to elaborate that actually, many times when ice melts, the density of ice is around one. It could be relatively less than that of the water it forms. So if it is more dense, it means the density has increased. I don't think the mass increases. But if the density increases, volume is equal to mass over density. If the density increases, it means the volume has decreased. So we can simply say that the volume decreases. Volume decreases. And if the volume decreases, it means work is done on the ice. So work is done. So work is done on the ice. Work is done on the ice. And heat is going to be needed to break the bonds. That means potential energy increases. So heat is needed, or thermal energy is needed to break the bonds. To break the bonds. So potential energy increases. Potential energy increases. Put in mind that change in internal energy is equal to Q plus W. Of course, work is done. The work done is positive because the volume decreases. So work done is positive. And even though there is no heat entering or leaving the system, as long as the work done is positive, there is an increase in internal energy because the potential energy component increases. So potential energy increases, thus internal energy increases. The internal energy increases. Okay, so when you get used to these equations, the explanations will become part of you. Next, the volume of some air assumed to be an ideal gas in the cylinder of a car engine is 540 centimeters cubed at a pressure of 1.1 times 10 power 5 pascals, temperature 27 degrees Celsius. The air is suddenly compressed. That is no time for heat to enter or to leave the system if it is suddenly compressed. No energy enters or leaves the gas by heating during the compression. That means Q is probably 0. The pressure rises to this value here, determine the temperature of the gas after the compression. So we just use PV over T is equal to a constant, or PV is equal to nRT. I'll simply use P1 V1 over T1 is equal to P2 V2 over T2. Then I want to find T2. T2 is going to be equal to P2. P2 is 6.5 times 10 power 6 times V2. V2 is, I don't need to change the volume because I know they will be cancelling. So V2 is 30 centimeters cubed. I will not change the units. Divide by P1, 1.1 times 10 power 5. Divide by V1. Divided by V1. V1 is 540 centimeters cubed. I know the centimeters cubed will cancel out. I'm just trying to make it to the subject without wasting time. So this is times T1. I'm bringing T1 this side. I took T2 this side. So I'm bringing T1 this side. So times T1, which is 27 degrees Celsius. That is 27 plus 273, which becomes 300. Press the calculator. So this is 985 Kelvin. You can also check. State the first law of thermodynamics. That is very easy. I can even simply say change in internal energy is equal to Q plus W, but note that there are two marks. So I can say plus W is equal to the heating of the system, or thermal energy transfer to the system, or heat transfer to, this is very important, to the system, or heat absorbed by the system or heat added to the system. Then I can say a plus W, that is work done on. This is work done on the system. Then I can choose a positive change in internal energy. This is an increase in internal energy. That is the first law of thermodynamics. Or you can simply say increase in internal energy is equal to the heat transfer to the system plus work done on the system. That would be the first law of thermodynamics. Use the law to explain why the temperature of the air changed during the compression. Use the law to explain why the temperature of the air changed during the compression. Remember, there was no heat entering or leaving the system. So we have already seen from the first law of thermodynamics, we have seen that we know that delta U is equal to Q plus W. And we said no heat enters or leaves the system, so Q is equal to 0. But again, there was a compression, the volume was decreasing, so the work done is a positive value. Because the volume was decreasing, work was done onto the system. So the change in internal energy is equal to the work done, and it is a positive work done. Since work is done onto the system, internal energy increases, which means the total kinetic energy of atoms increases, which means the average kinetic energy of atoms increases, hence increase in temperature. So I will simply say that since work is done on the system, work is done on what was it? Was it a gas? Since work is done on the system, internal energy increases. Internal energy increases. Remember, internal energy is equal to the total kinetic energy of the molecules. So, the total kinetic energy of the molecules increases, of atoms increases. The average kinetic energy of the molecules increases. Thus, temperature increases. So that is the simple account for that. You can think about it in formulas. First of all, Q is equal to 0 because there is no time for heat to enter or to leave the system. No time for heat to enter or to leave the system. So Q is going to be equal to 0. And on the other hand, work is done on the system because of the compression. Work is done on the system because of the compression. That means the work done, W, is a positive value, which makes the change in internal energy a positive value. A positive change in internal energy means an increase in internal energy. If the internal energy increases, it means the total kinetic energy of the molecules or atoms has increased, which means the average kinetic energy of the molecules has increased. And if the average kinetic energy of the molecules has increased, then it means the temperature has increased because temperature is directly proportional to the average kinetic energy of the molecules. Okay, so thus temperature increases. Next, State what is meant by an ideal gas. We said an ideal gas is a gas which obeys the equation PV is equal to nRT at all temperatures and pressures. So the gas which obeys PV is equal to nRT at all temperatures and pressures where P is the pressure of the gas. Pressure, my handwriting has become worse. P is the pressure of the gas. T is absolute temperature. T is absolute temperature. And then V is volume of the gas. Note that N times R are constants. N is the number of moles and R is the molar gas constant. Okay, next. An ideal gas comprised of single atoms is contained in a cylinder that has a volume of 1.884 times 10 power negative 2 meters cubed at a pressure of 2.12 times 10 power 7. The mass of the gas in the cylinder is 3.20 kilograms. Determine to three significant figures the root mean square speed of the atoms. Root mean square speed of the atoms. That is easy. We can use the general equation which is normally given in the list of formula. That is PV is equal to a third Nm mean square speed. Of course, we know that N times M is the total mass of the gas, which has been given as 3.8. Then we know that, what else have they given us? Okay, they have given us the volume. They've given us the volume. Yeah, I think that is enough. We can now find the volume is 1.84. So we can now find the mean. So the mean square speed is going to be the pressure, which is 2.12 times 10 power 7. The volume, which is 1.84 times 10 power negative 2. Of course, there is a 3 here. Divide by N times M is the mass. N times M, the total mass of the gas is N times M. So this will be over the total mass of the gas, which is 3.2. So this is 3.20 kilograms. Now I can press my calculator. So this is giving me a value such as 3,65700. Then I find a square root. C root means square speed is equal to the square root of 3,65700. So find the square root. And this is giving me 604.7. This was meters squared per second squared. Now when I get the square root, that is meters per second. Okay. The temperature of the gas in the cylinder is 22 degrees Celsius. Determine to three significant figures the amount in mole of the gas. Amount in mole, that is number of moles is equal to PV divided by R times T. So P is 2.12 times 10 power 7. The volume is 1.84 times 10 power negative 2. R is 8.31. Temperature is, they gave us 22 degrees Celsius. I think that is 295 Kelvin. Press the calculator. Okay, my calculator is giving me approximately 159 to three significant figures as required. 159 moles. Then the mass of one atom of the gas. The mass of just one atom of gas. Remember the total mass was 3.2 times 10 power, 3.2 kilograms. How many atoms do we, by the way, have in this number of moles? Remember, one mole has 6.02. One mole has 6.02 times 10 power 23 atoms. So it means total number of atoms is going to be the number of moles 159 times Avogadro's number 6.02 times 10 power 23. Now I want the mass of one atom. So the mass of one atom is going to be this number, the mass given, which was 3.2, divided by the number of atoms, which is 159 times 6.02 times 10 power 23. So we press the calculator very fast. So the mass of one atom is 3.34 times 10 power negative 26 kilograms. Then determine the nucleon number. I think as a chemistry student cannot fail to determine the nucleon number when they have the mass of the atom. Remember, the mass of the atom in kilograms can be converted into the nucleon number in a unit called unified atomic mass units. So just convert that mass from kilograms into unified atomic mass units. So this will be the same as the nucleon number A is going to be equal to 3.34 times 10 power negative 26 divided by 1.66 times 10 power negative 27. I'll round off this to the nearest whole number because it is a nucleon number. And this is giving me, this cancels. This is 33.4 divided by 1.66. That is 20. So this is approximately 20 U. So the nucleon number is going to be 20. I simply convert the mass from kilograms to unified atomic mass units. That would be the nucleon number. So the nucleon number is 20 for that atom. Okay. By the way, remember the mass of the atom is approximately the same as the mass of the nucleus, because according to the alpha particle scattering experiment, most of the mass is concentrated in the nucleus. Most of the atom is therefore empty what? Empty space. Okay, define specific latent heat of fusion. Fusion, that is actually melting. So the amount of energy required to convert 1 kilogram of a substance from solid to liquid, or 1 kilogram mass of a solid to liquid at constant temperature, is what we call the specific, that is 1 kilogram, latent, that is hidden, fusion, that is solid to liquid. So this is per unit mass, this is hidden, that is constant temperature, this is solid to liquid. So the thermal energy required to change the state between a solid and a liquid. Between solid and a liquid, thermal energy required to change the state. Let me add here, thermal energy required to change the state of a unit mass. That is 1 kilogram between a solid and a liquid at constant temperature. That is without changing temperature. So that is what we call the specific latent heat of fusion. It is precisely the energy required to convert 1 kilogram of a substance or of a solid to a liquid at constant temperature. To convert 1 kilogram, the energy required to convert 1 kilogram of a solid to a liquid at constant temperature. So the reason as to why I gave it like this is because even when it is liquid to solid, it is still specific latent heat of fusion. So it can be change of state between solid and liquid, either liquid to solid or solid to liquid. So it is still the same amount of heat. Although solid to liquid it might be required, yet liquid to solid it might be given out. So that is what we call a specific latent heat of fusion. Okay. Number next, they gave us an experiment. A student sets up the apparatus shown in the figure to investigate the melting of ice. Is investigating the melting of ice. The heater is switched on when the pure ice is melting at a constant rate. Pure ice is melting at a constant rate. The data shown in the figure are collected. So we have volume of the reading, voltimeter reading, ammeter reading, initial mass of the beaker, final mass of the beaker plus water. Time of collection is 5 minutes. The specific latent heat of fusion of ice is given as this. State what is observed by the student that shows that the ice is melting at a constant rate. State what is observed by the student that will show that the ice is melting at a constant rate. So if the student is to verify, or if you are to observe that the ice is melting at a constant rate, there are so many things that you could observe. Number one, if you were to measure the mass of the beaker and the water, it should be increasing at the rate of increase of the mass of the beaker and the water should be constant, or the level of water rises at a constant rate, or there would be a constant time between the drops which are coming from the funnel, or the volume of water in the beaker increases at a constant rate. All those observations will show that the ice is melting at a constant rate. So we can say, number one, I can say the level of water in the beaker increases at a constant rate. At a constant rate. That could be 1. Or I would say the volume of water in the beaker increases at a constant rate. Of course, the first one implies the second one. I can't state the two at the same time after even 1 to 1. Another person would say that there is a constant time between drops or constant rate of dripping. Constant, if the rate is the same, then there should be a constant rate. Constant rate or constant time, not constant rate. Constant time between drops from the funnel. Constant time between drops from the funnel. Another person would say, of course, when I say constant time between drops from the funnel, that is constant rate of dripping. Constant rate of dripping from the funnel. Okay, or we can say the rate of increase of the mass and the beaker, the rate of increase in mass of the beaker plus the water is constant. The rate of increase in mass of the beaker and water is constant. Okay, that one is finished. So any of those will tell that will be observed to show that the ice is melting at a constant rate. Use the data in the figure to determine the rate at which the thermal energy is transferred to the melting ice. Thermal energy is gained from the surrounding. Thermal energy transferred to the melting ice. Thermal energy transferred to the melting ice. So rate of transfer, that one is going to be the mass times latent heat of fusion. So let's say rate of transfer, how should I put it? Okay, thermal energy which goes to the melting ice should be the change in the mass of ice melting times latent heat of fusion, but we want the rate. And in the table, they have given us V and I, which will help us to find power, then times time, that is energy. So this is going to be equal to power times time. Power times time. So what I want is power, actually the rate of transfer to the melting ice. So the power is going to be equal to the change in the mass times the latent heat of fusion of ice divided by time. So this is going to be the difference in the mass, initial mass of the beaker plus water is 121.5. Final mass of the beaker plus water is 185. So there is a difference. The change in mass or the ice which has melted is going to be 185.0 minus 121.5. That is the ice which has melted times the specific latent heat of fusion, which is 3. This is in grams. I will not change it because I know the grams will cancel with the one for the specific latent heat. Divide by the time, but for the time I'll have to convert because the other one is joules per gram and the other one is grams, so it means we remain with the joules. So the other unit should be in seconds, so that is joules per second, which becomes the watt. So I will divide this by the time, which is 5.00 seconds times 60, minutes times 60. I'm pressing the calculator. Okay, so I am getting 70.3 watts. So that is 70.3 watts. You can also verify. Then thermal energy gained from the surroundings. Thermal energy gained from the surroundings. This is the one which is transferred to the melting ice. But what is supplied? Let's check what is supplied. Power supplied or thermal energy supplied. The power supplied is going to be equal to I times V. This is supplied. Power supplied is I times V, which is I was 12.8 times V is 4.60. When I press my calculator here, this is giving me 58.9 watts. So that is the rate at which power is supplied. So the thermal energy gained from the surrounding, the rate of thermal energy, rate at which thermal energy is gained from the surrounding. Since this is what goes into melting the ice, yet what is supplied is this, it means the excess contributing to this is obtained from the surrounding. So the rate from the surrounding should be equal to 70.3 and minus 58.9 watts. In other words, what melts the ice is equal to what is supplied plus what is absorbed from the surrounding. So when I subtract, so this is giving me 11.4. If I subtract it correctly, 70.3 minus 58.9. Yes, 11.4. That is the rate at which thermal energy is gained from the surrounding. In other words, the rate at which power is transferred from the surrounding to the ice. The power transferred from the surrounding to the ice. Next, an ideal gas undergoes a cycle of changes as shown. Before we even see the questions, we can look at the cycle of changes. It is pressure against volume. Along 950, the volume is constant. Here in your mind, you know that the work done is 0 because there is no change in volume. Along RP, you see that the volume is decreasing. So here you have in your mind that the work done is positive because the gas is compressed. Along PQR, the volume is increasing. So you have in your mind that the work done must be negative because the gas is doing work to the surrounding. So if you have those in mind, then it becomes easy for you to attempt the questions about these cycles. Okay, next, let's see what happens. At point P, the gas has this volume, that pressure, that temperature. Okay, the gas is heated at a constant volume and 97.0 joules of thermal energy is transferred to the gas. The pressure and the temperature change so that the gas is at point Q. Okay, we have seen point Q. The gas then undergoes the change from Q to R and then from R back to P. Note that therefore the total change in internal energy is 0. Total change in internal energy equals to 0 because we are going back to the starting point in one complete cycle. The gas then undergoes the change from point Q to R and then from point R back to point P. Some energy changes that take place during the cycle are shown in the figure. Okay, so then they are telling us, state the total change in internal energy of the gas during the complete cycle. Explain your answers. We are saying total change is 0 or there is no change. No total change in internal energy. For one complete cycle, there's no total change in internal energy because the final temperature is the same as the original temperature. Or you simply say the gas returns to its original temperature. Okay, then on the figure, complete the energy changes for the gas P to Q, Q to R, R to P. So let's go back to the figure. P to Q, they have given us thermal energy transfer to the gas, that is positive. P to Q, if you remember P to Q, the volume was remaining constant. P to Q, volume is constant, no work done. So work done is 0. So here I will just add a 0. Then increase in internal energy is just the sum. So increase in internal energy is equal to Q plus work done. So we sum up. This gives us positive 97.0. Then Q to R, increase in internal energy is still the sum. So we sum up this. This gives us negative 42.5. Then remember the total increase in internal energy should be 0. When I add up the last row, I should get 0. So negative 97.0 plus negative 42.5 plus a value x should give me 0. So what is x? So I find x. Now remember this is positive, not negative. So this is negative 54.5 joules. X is negative 54.5 joules. Then I move upwards. Remember, using this, the change in internal energy is negative 54.5. This should be equal to the heat supplied, which is not known, plus the work done, which is 37.0. When I take this one across, it becomes negative 54.5 minus 37. So this is negative 91.5. These questions are very easy. If you master them, the logic of using the first law of thermodynamics, they become extremely easy. Okay, so we have finished this part of the question. Next, the fixed mass of an ideal gas is at a temperature of 21 degrees Celsius. The pressure of the gas is 2.3 times 10 power 5 pascals, and its volume is 3.5 times 10 power negative 3 meters cubed. Calculate the number of molecules. This is very easy. PV equals to N number of moles RT. Remember, number of moles is the number of molecules divided by Avogadro's number, then times RT. So from there, I can even find the number of molecules, even if I don't add, I don't substitute R over Na with K. So the number of molecules is going to be P times V times Na divided by R times T. Substituting, the pressure is 2.3 times 10 power 5, then times the volume, which is 3.5 times 10 power negative 3, times Avogadro's number 6.02 times 10 power 23, divided by molar gas constant 8.31, temperature, the temperature is 21 degrees Celsius to Kelvin units, that is 294. Press the calculator to get the answer. So N is 2.0 times 10 power 23. N is 2.0 times 10 power 23. Then the mass of one molecule of the gas is 40 U. Perhaps that is argon. Determine the root mean square speed of the gas molecules. The mass of one molecule is 40 U. determine the root mean square speed of the gas molecules. So let's find this using the simpler expression given in the list of formula. PV is equal to a third n times m mean square speed. So I can find the mean square speed first, which will be 3 times the pressure. The pressure is given as 2.3 times 10 power 5 times the volume, which is given as 3.5 times 10 power negative 3, divide by um, the number of molecules. We have obtained them above there, which is 2.0 times 10 power, I think, 23, times the mass of one atom, which is 40 U. That will be 40 times, remember, small m is the mass of one atom, capital N is the number of molecules. So 40 U is 40 times 1.66 times 10 power negative 27. So we can press our calculator here. So the mean square speed I'm getting is approximately 18,200. 18, no, not 2,000. Then I find the square root. And the root is 400, and so C root mean square is the square root of 18. By the way, this is meters squared per second squared. Root of 18, 2000, that is 426.6. So this becomes approximately 430 to two significant figures. Okay, then the temperature. Oh, by the way, you would also find the answer to that using the simple relation that I have. M mean square speed is equal to 3/2 kT. As an assignment, you can try to see if you can find the root mean square speed. Part B. The temperature of the gas is increased by, this is the increment. It is not the temperature, but it is the increment. So you must note that. The temperature, so it means the new temperature is going to be, the temperature here is going to be equal to the initial temperature was 21 plus the new temperature is plus the increment, which is 84. Then I change this to Kelvin, that is plus 273, which gives us 103 and 5, that is 8. So this is 378 Kelvin. That is the new temperature. The initial temperature is 21. The increment is 85 plus 273 to change it to Kelvin. So calculate the value of the new root mean square speed of molecules over the original root mean square speed of molecules. Remember, the mean square speed was directly proportional to temperature, meaning that the root mean square speed is equal to a constant times the square root of the temperature. So I'll put the new on top. So the root mean square speed of the new is equal to a constant, the root of the temperature, which is the square root of 378, divide by the old root mean square speed was 430. We have calculated it there. This will be a constant, divide by the root mean, the square root of the old temperature, which was 21 plus 273. 21 plus 273, that is 294. So we want that ratio, or we just want the ratio. We don't need to multiply by 430. We just want the ratio. So we need this ratio here. You just find the ratio is going to be the square root of 378 divided by 294. Okay, my ratio, the ratio I'm getting is 1.1. So I think that is true, 1.1. Okay, next. Using a simple kinetic model of matter, describe the structure of a solid. Describe the structure of a solid. A solid. Using the simple kinetic model. I think we described this. So we know for a solid, the molecules are very close together and they are arranged in irregular repeating patterns which are called lattices. We say these molecules vibrate about their fixed position. We have described the structure of a solid. So the molecules are very close. Molecules are very close together, are tightly bound together. Molecules are tightly bound together. Molecules are tightly bound together and arranged in regular repeating patterns. Regular repeating patterns called lattices. Patterns called lattices and vibrate about their fixed position. Vibrate about a fixed point or a fixed position. So we have explained the structure of a solid using the simple kinetic model. When they talk about kinetic, you should explain in terms of molecules. Then part B, the specific latent heat of vaporization is much greater than the specific latent heat of fusion for the same substance. Explain this in terms of spacing of molecules. So there is going to be much greater spacing or increase in volume during vaporization compared with fusion, as simple as that. So there is much greater increase. Much greater, this is the most important word. Much greater increase in spacing. There is much greater increase in spacing of molecules during vaporization compared with fusion. So during vaporization, the work done is more because the volume increment is greater, since a lot of work is done to push against the atmosphere as the molecules escape from the liquid to the vapor phase. So that much greater increase in spacing would require more energy to completely break the bond so that the molecules can escape from the liquid into the vapor phase. Okay. The next, a heater supplies energy at a constant rate. The mass is 0.045 kilograms of a substance. The variation with the time of the temperature of the substance is shown in the figure. So here we have the variation. Before even reading the questions, you can know that when the substance is being heated, that means initially its temperature rises at T equals to 0, we are somewhere here. Its temperature rises, then it becomes constant. So something must be happening here. There's a change of state, and most likely this must be melting. Then here the temperature again rises, and again there's a change of state. Most likely this could be boiling or vaporization, not necessarily boiling, but vaporization. So this could be most likely vaporization. Okay, so they are saying determine the temperature at which the substance melts. Just look at the graph. The temperature, I think it is melting at negative 100 degrees Celsius. So just substitute, just write here negative 100 degrees Celsius. Then the power of the heater is 150. Use data from the figure to calculate in kilojoules the specific latent heat of vaporization of the water. So the heater is supplying heat. So we say power supplied is going to be heat supplied is going to be power times time. If all this goes to melting, vaporizing the water, so this will be the mass times the latent heat of vaporization. So the latent heat of vaporization is going to be the power times time divided by the mass that has vaporized. So this is going to be, the power is given as 150 for a time of, which time should I use? During vaporization from the graph. Let's see vaporization. So vaporization starts at this point here and it stops at this point here. This is in the center, in the middle of the two boxes. So I think that is 8 point something. That is 8.5. And this is here. That is 3. Yes, that is 3. So vaporization is occurring for that time. So this will be between 8.5 minus 3.0. But that is in minutes. I multiply it by 60 to change it to seconds. Then divide by the mass, which is 0.045. I press my calculator. So this is 1,100,000. But they want the answer in kilojoules. So I divide by 1,000. So it becomes 1,100. It is 1,100 kilojoules. Okay. Then suggest what happens. Suggest what can be deduced from the fact that section Q on the graph is less steeper than section P. Remember now section Q, it is already gas. Section P is already liquid. So this is a liquid. This part was solid. This part was liquid. And the last section, this is gas. So they are saying suggest what can be deduced from the fact that section Q on the graph is less steeper. That means it has a smaller gradient. That means it takes more time to increase its temperature as compared to section P. So what does that imply? Section Q is less steeper than section P, meaning section Q will take more time to increase its temperature by a small change. Yet section P takes a shorter time to increase its temperature by a greater change. That means the gas must be having a higher specific heat capacity. That means the gas would require more energy to raise its temperature by 1 Kelvin. That's what it means. The one which is less steeper means it will require more energy to raise its temperature by 1 Kelvin. That's why you said water takes long to warm up, or its temperature, it takes long to increase its temperature. That means it has a higher specific heat capacity. Yet the land takes a shorter time to change its temperature, so it has a lower specific heat capacity. So we can simply say that the gas has a higher specific heat capacity than the liquid. In other words, the gas requires more heat to raise its temperature by 1 degree Celsius. So we simply say that the gas has a specific higher specific heat capacity than the liquid. Okay, next let's end with this. We shall finish this in part 4. Part 3 will end on this question, on this part here. Show that the number of gas molecules is given by this. The volume initially is that, at a pressure of that, and the temperature is that. So PV is equal to nRT, which is going to be number of molecules over Avogadro's number times R times T. So I want N. N is going to be PV times the number of Avogadro's number divided by R times T. We substitute. P is 3.3 times 10 power 5. V is 1.8. 1.8 times 10 power negative 3. Na is 6.02 times 10 power 23. Then we divide this by R, which is 8.31 times the temperature, which is 310. So this is going to give us the number of molecules. Let's check. Okay, so I'm getting 1.4 times 10 power 23. You can also verify. Okay, let's start from this very point in part 4. See you in part 4.